Good morning, everyone. Thank you all so much for joining us today. I am not Courtney Battle. My name is Susan Ortiz. I am the program director here at Hand. Um, Thank you all so much for joining us for part two of the Electrification and Healthy Housing Solutions webinar series. If you are unfamiliar with Hand, we are the Housing Association of Nonprofit Developers. We are a nonprofit membership association for community development and affordable housing professionals spanning from Richmond all the way up to Baltimore. We're so excited to partner with NHT on part two of this series that's addressing how we can build more equitable communities through healthy housing outcomes. If you missed part one, that is available on our YouTube, and we can drop a link for that in the chat shortly. But we are excited today to address ventilation. Again, thank you to our partners at NHT who have brought these sessions to us and help us build out some really great content for you all today. And thank you to our speakers, Jonathan and Adam, who you'll hear from later, for sharing their expertise on this. I know I'm excited to learn a lot today, and I can guarantee that you all will as well. Just quick housekeeping things. The chat and the Q&A box are enabled for you all. So throughout today's session, feel free to drop your questions or comments in the chat or the Q&A box. Myself and Leslie will monitor those throughout today's session and answer those where needed. And we'll also have a dedicated section for Q&A at the end of today's session. So definitely feel free to bring your questions while you have these experts in the room. Take advantage of their willingness to share today. But thank you again for joining us, and to our speakers. Without further ado, I will toss it over to Leslie Zarker at NHT, who's going to set the stage for today's session. Thanks, Leslie.
Thank you, Susan. It's great to be here. Hi, everyone. I'm Leslie Zarker, Director of Sustainability Policy at National Housing Trust. First, a bit about, next slide, please, sorry. First a bit about National Housing Trust. We're a national nonprofit. We work to create and preserve affordable multifamily housing for underserved families. Our home base is Washington, D.C., and we own a portfolio of 4,000 multifamily units across 13 states and D.C. And we have a dedicated resident services team that provides on-site services to support residents in those communities. We're also a community development financial institution, or CDFI, and I am part of NHT's policy innovations team. Next slide. Today's webinar is Getting Ventilation Right, Understanding and Controlling Airflows in Multifamily Buildings. And as Susan said, it's part of our three-part series. On November 6th, we'll have pests, mold, and muck, cost-effective strategies to remediate indoor air allergens in multifamily affordable housing. And we'll present case studies there on proven strategies to control cockroaches and rodent infestations, as well as to identify and remediate sources of plumbing leaks and water intrusions. And then last October 17th, we heard from experts on heat pump and electrification solutions in affordable multifamily housing. And if you missed that, you can view the recording by going to handhousing.org and navigating to the page at the bottom of the screen here. And I think Susan is also dropping the link in the chat. So these three topics really do complement and build upon each other. And they're really integral to realizing our goals as affordable housing developers to create safe, healthy, and affordable homes. So I hope that you can join us for all of these webinars. Next slide. Today we'll hear from our wonderful panelists, Jonathan Wilson from National Center for Healthy Housing and Adam Romano of the Association for Energy Affordability. And they're going to help us demystify indoor air quality in multifamily buildings, focusing on best practice strategies for retrofitting ventilation systems that control airflow, reduce air leakage in multifamily housing, which is especially timely as we plan electrification upgrades of HVAC systems. So next slide. I'd like to provide a little context for the genesis of our program, the DC Healthy, Green, and Affordable Housing Program, and also for this webinar series. Next slide. this slide, sorry. Our pilot projects are to retrofit 6 properties, primarily in wards 7 and 8 in DC, for electrification, energy efficiency upgrades, and to improve health outcomes for residents. Our goal is that nearly 800 families across these properties will benefit from housing that is climate resilient, energy efficient, and free of sources of indoor air pollution, and also affordable, of course. So we're taking an integrated approach over the next couple of years. We're supporting building owners by providing financial and technical assistance. A core principle of our project is to engage residents early to understand their priorities and concerns with green retrofits. And we know a well-trained workforce is critical to reaching clean energy goals. So we aim to create mentorship opportunities for small and minority business contractors in DC. And we're partnering with local community groups. So key partners are Children's Law Center, Children's National Hospital, and Latino Economic Development Center. Next slide. So what's driving this work? A key driver is the unhealthy housing conditions that lead to poor health outcomes for residents so frequently in affordable housing. And to address that, we've partnered with Children's National Hospital and Children's Law Center to specifically target properties with a high prevalence of children with asthma living in them in our Healthy Green Affordable Housing program in DC. So this slide provides some context for that. 10% of DC's children suffer from asthma. That's actually quite high. It's nearly the highest rate by state for pediatric asthma nationwide. Even worse, these cases are concentrated in communities of color. So the map on the left here shows childhood asthma rates by zip code. And the highest rates are in deep blue in wards 7 and 8, which are the historically redlined districts of DC, where also the largest communities of color are located, as you can see on the right-hand map. And I just want to mention another stressful problem for DC's low-income households is their outsized energy burden, especially compared to non-low-income peers. Low-income households in DC spend over 7% of their gross income on utility bills, compared to 2% on average for non-low-income households. Next slide. So poor indoor air quality, that is, of course, a key contributor to childhood asthma. And of course, ventilation is a critical factor in maintaining high indoor air quality. In multifamily buildings, we know it can be difficult to control the flow of allergens between units in the building. There's dust mites, cockroaches, dander. Poor ventilation leads to stuffy, stale air, which is a buildup of carbon dioxide and other harmful gases, as well as leading to increased humidity levels that can cause excessive moisture and then mold. Again, a potent asthma trigger. And then there's gas stoves. There's evidence that gas stoves cause 12.7% of childhood asthma nationwide, according to the Journal of Environmental Research and Public Health, as gas stoves emit nitrogen dioxide and particulate matter, both of which exacerbate asthma. So, of course, quality ventilation draws fresh air into the building, while also filtering and expelling indoor pollutants and maintaining healthy humidity levels. But we know there's a lot of challenges in maintaining quality ventilation in multifamily homes, where there's often limited space available for things like ductwork, makeup air, and exhaust fans to ensure proper air circulation and exchange. So with that, I am going to pivot to our experts on ventilation and indoor air quality and how to deal with these challenges. I'll just remind folks to drop your questions anytime you think of them into the Q&A box or the chat boxes with the icons at the bottom of your screen, and we'll address them at the end of the presentations. So our first speaker today is Jonathan Wilson. He is Deputy Director of the National Center for Healthy Housing, where he's managed research, technical assistance, and policy projects since 1993. Jonathan helped coordinate the evaluation of the HUD Lead Hazard Control Grant Program, the largest, most comprehensive study of lead hazard control in housing ever undertaken in the U.S. His current work includes assessments of the effects of ventilation and energy efficiency on resident health. So welcome, Jonathan.
Thank you, Leslie. It's a pleasure to be here. Adam and I actually had an opportunity to present together this spring, and I just want to give you a background. My presentation is going to be on sort of expanding on what Leslie was talking about, the importance of ventilation, the indoor air, the challenges we have in the indoor air, and then giving you a sense from a study that we did of the benefits of ventilation. But we presented that a few times, and we'd often get a response that, this is great, but it costs too much and it's too hard. Most of our buildings are already built, and retrofitting for ventilation in multifamily housing can be a challenge. And I was really impressed by Adam in the spring in just making it doesn't sound as onerous and as challenging as many make it out to when he goes through his presentation. So I think that mine really leads into what he's going to be telling you. And I just want to say that I lead a team of researchers at NCHH. I'm proud of them. And a lot of this work is through their work as well. Next. So I just want to start off by saying that housing is more than shelter, that it's a place where we want our kids to grow up, where we gather, where we gather as family, as community, and where we want to grow old. And while this presentation is going to be a lot about, building as four walls and how to move air in and out, we need to continue to remember that is what housing is all about. And we like to say at NCHH that if it's not affordable, it's not healthy. But if it's not healthy, then it's not affordable. And that is our North Star, is that we need to understand what's making us unhealthy in our housing and take steps to remediate it. Next. But at its core, housing is and must be shelter. It has to keep the wind and the rain and the snow and the ice out. It must, at best it can, keep the heat and cold at a reasonable level from kind of getting in. It must keep the pests and other intruders out. And it needs to, when we provide heat and cooling, it needs to keep those in. That's basic energy efficiency. And so we need to build it tight. Next. We need to build it tight, but not too tight. We can't be in a bubble. And we need to recognize that we need doors and windows and lots of different reasons why there are going to be cracks and crevices in our buildings. So we need to figure out how we can get it to the best we can. And there's another reason why we don't want it to be too tight. Next. The Puebloan people understood that when they built their kiwas, that they would have, ceremonial fire to keep them warm. They needed a smoke hole to let the smoke out, and they needed a ventilation shaft to bring the fresh air in. And they were great designers of this with the products and the materials they had to use at the time in the desert Southwest. So we've known this for a long time, and we just keep needing to relearn this for the new buildings that we build. Next. So this is a complex slide. And if you're already into building ventilation, you'll understand some of this already. But just as the Puebloans understood that there are building dynamics that we can draw fresh air in as we're heating our air, it's going to be pushing up out through the hole in the roof. And if we have a hole on the side that's going to bring the cool air in and the fresh air in, it's, the pressure dynamics are going to help us. And in this case, if we have a multi-story building, there's one part of it, which is the stack effect. Our buildings act sort of like chimneys, and the heat in the building is going to be pushing up. And this happens to be an example of a building in Canada in the winter. And so there's cold air outside, there's heat inside. The cold air is being drawn in through the bottom levels. It happens to be, if it's near the road, is probably bringing in the pollutants that are from the cars and the trucks that are outside at the same time. It's being drawn up through the building and pushed out through the roof. At the same time, on a windy day, we've got pressures on one side of the building pushing through the building. And so it's creating dynamic in that way. And then the third box, this is a mechanical ventilation system that's been used a lot in some buildings, where we pump air in from the roof into our building corridors. And I think we think that when we push this air in through the corridors, it's going to leak in through the units, giving fresh air to all the units, and then it'll just push out to the sides of the building. And that's going to be the way our fresh air is going to get in, and the contaminated air is going to be pushed out. But in fact, all these three dynamics work together, and it creates this interesting exchange of air through the building, where we've got air coming in one side of the building, but also up through the bottom, and it's pushing out one side more than the other, and is definitely pushing up through the building, creating these dynamics where if somebody happens to be smoking on the bottom floor, it's going to be pushing up through the building, and people on the top floor are probably going to smell it. And at the same time, if we've got cooking going on, that cooking is going to be pushing up through the building, and all the good things and bad things in that cooked air is going to be coming through the building. And so this is why we have to think about how we ventilate and how we design our buildings, so that we are, preventing people from being exposed to lots of different contaminants, whether it's from the outside or from the inside, and creating problems with their health. Next. This is probably the most complex of the slides I have, but there was a meta study done in 2021 looking at multiple studies like this, and others were looking at airflows through multifamily buildings. Where is the air going? And what they found on average, and this is on average, it's highly variable across buildings, but on average, the airflow in a building, about a little over a third of it was moving outdoors from a single dwelling. About a little less than a third was moving into the corridors as air flowed. About the same amount was moving up and down. What we're just showing you with the stack effect, that on certain days it's going to be moving up. On a warm summer day, actually, with air conditioning, the air pressure is going to be dropping down, and your air is going to be going downward instead of upward. And so we've got a lot of movement between units above and below you. And actually, somewhat surprising, only about 6% of the airflow is moving into a neighboring unit on the same floor. So the airflows, when we smell things in our apartments, it's coming usually from the top and the bottom, moving through the units. But in a single family home, most of the dynamic we think about is indoor air coming in and out from the outside. But in multifamilies, we've got a lot of different places where this air can be flowing. And as I said, it's highly variable. So this slide on this figure on the right is showing leakage to the outside from the interior as a percentage of the total leakage. And so on the left of this figure, we see a very tight building. Not much is getting outside. There's not much variability between the units, and most of the units are at a low level of amount of air that's going outside. So this is either a new building or well-designed, energy-efficient unit that's been retrofitted. But then when we get into the middle of this figure, we see, there's not much air getting outside, 25%, but there's high variability. And this is again, going back to that stack effect. You may have the units in the higher level stories that where the air is really pouring out. And then you have some in the lower levels where there's not much going out because most of it's coming into the unit from the outside and going up. And so there is a lot of dynamics that go on with our buildings, and this is moving the pollutants within the units to lots of different places. And our pollutants these days are not as simple as in the Pueblo and Kiwa, where it was smoke. Next slide. Oh, sorry. One other thought on this before we get to the next slide. So solutions to this, we know we can tighten the building envelope. It's a more energy efficient building, and that provides better support for our shelter. In addition, we can compartmentalize, create basically little units within each other where there's little shelters. So the air is not moving as much between units, up and down especially, so that we're reducing both the heat and cold that we're losing from our units, but also keeping the contaminants out and moving our contaminants up through ventilation. But in order for tightening and compartmentalization to work, we need to make sure we have proper ventilation. So it's not only build it tight, but ventilate right. Next. So our indoor pollutants today, next. Some of them come from our building products. We're doing better at some of these things. We now have rules and laws reducing the amount of wallboard or other wood board products that have formaldehyde in it, but that was a real problem. That formaldehyde is a carcinogen that we don't want in our housing, and so we're doing better with that. Next, we have consumer products that we use in our homes or store in our homes that can be off-gassing lots of different bad things, and so we need to be concerned about that. Next. We do things in our homes, some that smell good and some that don't smell good. Some are good for our health and others that aren't, that are combustion. And we're creating small particles, we're creating contaminants. The things that Leslie were starting to talk about that come off of our cigarettes and our incense are chemicals that are creating problems to our home environment. And next. And Leslie started talking about gas stoves, and the natural gas that is burned is not completely burned. So, in an ideal world, what the industry will tell you is just going to turn into carbon dioxide and water, and it's all going to be good. But we know that with incomplete burning, it also creates nitrogen dioxide, it creates formaldehyde, it creates carbon monoxide, and many other things are coming off these stoves. Some of it doesn't even burn at all and just produces methane in the air. So we need to figure out how to make sure that these pollutants are properly being moved out of our space so it's not harming our health. Next. One of the things that is the biggest that we think about is cooking. Recently, the Department of Energy did a survey, and they released it I think last year or the year before, that talked about how often people cook in their apartments, and 74% reported that they cook at least one hot meal a day, and 53% cook 2 or more hot meals a day. And the same survey found that 42% of cooking ranges in apartments use gas. So this is not a minor issue. Whether it's gas or electric, there's a lot of things that are coming off of the stove. And we need to think about how we're moving those particles, those pollutants out of the space and into the outside air. Next. But I just want to caution that while cooking can create pollutants, it should not be discouraged. The alternatives of going out to eat, of bringing a microwave meal, often these are creating great calories. They're creating high levels of sodium, high levels of saturated fat, high levels of cholesterols that are also bad for us. So we need to create spaces that encourage cooking at home. We want the levels of cooking within apartments to actually increase. It's higher in single family homes. We want it to be higher in apartments. So how do we do that? How do we encourage cooking without creating problems for ourselves? Next. So let me give you a case study. This study is a full-blown study. It's not just a case study, but I call it that for this presentation today. This was a study we did in New York City and Chicago, multifamily housing. The purpose of the study was to determine the effects of continuous mechanical ventilation on the indoor air quality. To look at this, all the dwellings had to have a working gas stove, and they'd also gone through a green rehab within the past 8 years. Mainly, they met the enterprise green criteria, community criteria, but any green standard would do. So these were, well-performing homes that were part of this study. Next. We wanted to assess the effect of ventilation on indoor air quality. We went and did indoor air testing 3 times over an 8-month period. We wanted to look at it in different seasons. We wanted to get multiple visits so we could see the effects of usage on the space over time. And the study group was designed to meet the ASHRAE, the gold standard for ventilation, 62.2. Comparison group was not designed to meet it. And so it was mechanical ventilation was required to meet the ventilation standard, where in the other units, it was either a low level of mechanical ventilation or it was dependent only on windows to provide the ventilation and meet the code in the community. Next. So what were we concerned about? Particulate matter, small particles that can get deep into the lungs and can create respiratory health effects and cardiovascular effects over time. And this is true with cooking in general. It's also comes from smoking and other things. But for cooking, whether you have a gas stove or a electric stove, if you're heating at high heats and you're creating small particles from the burning cooking process, it's going to be creating particulates in the air. There are other contaminants that are coming off of the gas stoves that are combustion byproducts, nitrogen dioxide, carbon monoxide, carbon dioxide. Carbon dioxide is what we breathe out. And so most of the carbon dioxide in the air is from either outdoor air or from what we are breathing in the unit, but it can also be produced from the combustion process. And then we have formaldehyde, a carcinogen that can be a byproduct when you're using gas stoves on low levels. And I think that Leslie mentioned that nitrogen dioxide is an irritant and a chemical that can really affect our lungs and can not only cause asthma attacks, but it's been associated with asthma, causing asthma. So these are all factors that we have to think about while we're trying to improve the health of people in the house. Next. So the study group had continuous bathroom ventilation as exhaust ventilation. So it wasn't balanced ventilation where there was some supply air coming in and the exhaust was going out. This was just exhaust. So any makeup air was coming in through the cracks and crevices of the building. But it was designed to have the proper airflow. So it was moving enough air to meet the ASHRAE standard. 20% of the study units also had continuous kitchen ventilation, again, exhaust ventilation that was ducted to the outside. So this was rooftop exhaust fans that was drawing air out of the units up through the kitchens and up through vents to the roof. And the comparison groups, as I mentioned, either didn't have continuous ventilation or didn't meet the criteria. Next. We controlled for lots of confounders. We asked that smokers not be included, but we did find that some people did smoke in their unit, but we tested for nicotine to control for those levels. We asked people not to open their windows during sampling, but we also knew that some people would, and so we checked for actual window usage through interviews. We reported and had interviews about how many meals they cooked, the number of occupants, whether they left doors open, whether they turned on their ventilation on-demand settings, if they used room air cleaners, and any other behaviors that might affect air quality. And then we also controlled for season, for outdoor air quality, the type of building, and we looked at musky odors. Next. And what did we find? We found that for particulate matter, we saw improvements. We saw improvements for carbon dioxide and for formaldehyde. And this was overall in general, when we compared the study group to the comparison group. So overall, this ASHRAE ventilation was successful for a number of these contaminants. Next. For carbon monoxide and for formaldehyde, for the kitchen exhaust, we found significant large effects from this. So we were seeing improvements for these two measures as well. Next. So overall, we saw that with this continuous mechanical ventilation, we reduced the levels for 4 of the 5 contaminants over the non-continuous ventilation, the just opening windows or something that you had to switch on and off by yourself. The only thing we didn't see an effect was for nitrogen dioxide. We thought that there may have been indoor air reactions. These were, highly, higher polluted cities than others in the country, and there were outdoor air influences. Interestingly, we did another study in single-family homes, and we saw effects for ventilation using ventilation over the stove on nitrogen dioxide. So it's a different, that was not done in as much as in cities. It was done across a number of different places. So ventilation can have an effect. It just didn't have an effect on nitrogen dioxide in this study. We saw that the air exchange rates were higher, so we believe it was the ventilation that was having the effect. Bathroom ventilation improved the particulate matter and the carbon dioxide, while it was, even better when we had the kitchen exhaust ventilation for CO, carbon monoxide, and for formaldehyde. Next. So the report is available. If you just go to our website and search stove, it's there. So if you don't have time to write this down quickly, we have that available. And next. And I just want to thank our funder, the JPV Foundation. We were the coordinating center for the study, but we had partners at the University of Illinois, and we had partners at the Icahn School of Medicine at New York City, and our main partner was Enterprise Community Partners, who helped coordinate this project overall. We were the research coordinator; they were the overall coordinator, and we couldn't have done it without any of these partners. So I want to thank you. So as I said, this is a lead-in to give you a sense that ventilation really is important. We need it in our multifamily housing. It can have an impact on our indoor air quality. And with that, I want to turn it over to Adam to tell us how we can do it.
I'll just provide a few words of introduction for Adam. Thank you so much, Jonathan. That was really helpful to set the stage today. Again, please go ahead and drop your questions into the chat box, and we'll try to get to them as we can. Adam Romano is the Senior Director of Workforce Development and Training at the Association for Energy Affordability. Adam has provided research, consulting, and design services for commercial, multifamily, and residential buildings. He's led many training and workforce development initiatives that are designed to expand the national talent pipeline for energy engineering and clean energy technology. Adam's delivered over 150 educational sessions on varied technical topics, ranging from heat pump design and installation to high performance building construction. So welcome, Adam. Thanks for being here.
Yeah, thank you very much, Leslie. And thank you, Jonathan, for that information on that study. And I'm going to start talking about some of the solutions to how do we need to, or how we can improve ventilation systems in multifamily housing. Next slide. Before I jump into that, I just want to talk a little bit about the Association for Energy Affordability. We are a mission-driven, non-for-profit organization, and our goal is to improve the energy efficiency and health outcomes in affordable housing. And we do that through the variety of the programs you see on the bottom left corner here. Policy work, training, research and development. And then two of the areas that I'm going to focus in on for this presentation are the Weatherization Assistance Program and our Technical Services programs. In these two programs, we are addressing ventilation in multifamily buildings. For those of you that are familiar with the Department of Energy's Weatherization Assistance Program, one of the requirements is to meet the ASHRAE 62.2 standard in both single-family homes and multifamily buildings. So through our implementation work in weatherization, we have to be innovative and come up with solutions to address maybe some of the deficiencies in ventilation systems that we find in New York City as well as in California. That's kind of where our offices are based, both in New York City in the Bronx and in California in the Bay Area. Next slide. So before I jump into the solutions, I just want to talk a little bit about the ventilation system types that we see in multifamily buildings. Next slide. So around the country, especially you look at older housing stock that was built prior to World War II, you see a lot of buildings that were designed to have natural ventilation. So what Jonathan was mentioning, that there's a lot of interactive effects and a lot of driving forces that impact our buildings and our homes that force air into and out of our buildings through stack effect, mechanical effect, wind effect. In this case, it'll just be stack and wind. And buildings were designed to take advantage of those interactive effects to provide ventilation to kitchens and bathrooms. So by building design, kitchens and bathrooms needed to have access to an operable window, and that operable window in most cases was sized with a free area opening that had a relationship to the floor area of the kitchen or the bathroom. So the idea was when you're cooking or using the bathroom, you were supposed to open the window to allow air to come in or to come out of that particular room. And sometimes they were also designed with a vented skylight. You can see in the stairwell on the right-hand side of that particular building drawing that there's a vented skylight there as well to help induce airflow to help improve or increase stack effect to bring air into the building. Next slide. Now, there's some advantages and disadvantages to this approach, right? The first one is that it's inexpensive. There's no maintenance, right? Because there's no mechanical system to maintain. It's inexpensive because we don't have to, provide a system to control ventilation in buildings. It's not space intensive, right? These are the components that we're going to install anyway. We're not, routing ductwork or having vertical chases through the building. And it's energy inefficient in a sense that it is not utilizing any type of energy to run fans or associated components. But there's a whole host of disadvantages, right? One of the things that we find with these types of buildings is that airflow rate and pattern it's not constant, it's not predictable. There might be times where you are cooking and you're not getting a lot of stack effect because the interior temperatures and the exterior temperatures are fairly close, right? We need a large temperature difference between the inside and the outside to drive that stack effect. So we might have times where we don't have a lot of airflow. It's not a windy day. And even if the window is open, we might not be getting enough airflow into those spaces to dilute those contaminants or to remove those contaminants from those areas where pollutants are generated. There's no control. So again, it depends on those driving forces. So there might be, to Jonathan's point, areas of the building that have high rates of ventilation, such as, the bottom of the building and the top of the building. But what about the folks that are in the middle? They might not be seeing a lot of ventilation on those days because they're not at the extremes of the building, top or bottom. It depends on occupant intervention. That's one of the biggest disadvantages, especially in the wintertime. Not many people are going to want to open their windows when it's, 5 degrees outside when they're cooking or when they're utilizing the bathroom, right? So occupants have a big impact on how much ventilation is taking place. And arguably, those are the times where you might need the most ventilation because all the windows are closed and you might be inside more often during the wintertime. The incoming air cannot be filtered, right? There's no filtration mechanism. So if we're, bringing in outdoor pollutants, right, there's no way to remove those or to treat those or to exclude those. So it doesn't really work with that. And heat recovery is not feasible. We'll talk a little bit about heat recovery as later on. We're not going to be able to recover any of the indoor heat with these types of systems. So there's a whole host of disadvantages, with this type of approach. Next slide. And then as building codes progressed and we started to see that there is an impact on indoor air quality, when we don't have means of mechanical ventilation, we started to see mechanical ventilation being installed in buildings, right? And it comes in two different forms, right? We might have local spot ventilation like this, where we have vented kitchen range hoods, we have vented bathroom fans, because again, the ASHRAE standard, there are areas in a building, in the dwelling units. There's also areas outside of the building or outside of the dwelling units that also need exhaust ventilation. But there's areas inside of the dwelling units that, because of their function, kitchens, baths, they require exhaust ventilation. So we started to see that, being implemented in buildings, right? And, now we're removing the contaminants at the source, at the generation source, and not allowing them to, permeate through the building and work their way out into the hallway and make their way up that skylight, right? We're trying to catch them at the source so we can try to have a positive impact on our indoor air quality. So you start to see these come into play. Next slide. So there's some common problems with these as well. The earlier ones that were installed were very loud. We had fans that were meeting or exceeding the 1 zone requirement we see now with the ASHRAE standard. And because of the noise that they generate when they're in operation, you saw that, again, occupant behavior has a big impact on ventilation, that they're not being utilized. So even though they're there, they're piped in, they're vented, they're ready to go, they're providing the right flow rates, if they're going to become a distraction or a nuisance, they're not going to be used, right? So we need to be able to control for occupant behavior as well. The older ones were very susceptible to dirt, and you start to see issues with, degradation in performance as they became, dirty or compromised. Some of the earlier equipment wasn't very robust. The industry was providing a base, solution, but we've definitely advanced since then. But some of them were cheap, so that we saw high rates of failures. There was poor installation quality. That's been one of the biggest issues that we've found when our implementation work with ventilation systems is that, they're not really, they're an afterthought, right? I'm not, not saying they're always an afterthought, but in a lot of cases, you pay a lot of attention to heating and cooling because, folks will complain. There's not as much, emphasis put on ventilation systems in terms of the installation. So we see a lot of deficiencies there. And then there's limited control options for these. So there's lack of efficiency, lack of use, because of the control methodologies that they were utilizing. Next slide. And then as we get into, larger buildings, we get into buildings that now have stacked units, right? You start to see that there's a shift from localized equipment to more centralized equipment. So this is very, very true with larger buildings. When you get into mid-rise and high-rise buildings, especially, you start to see the move towards, central heating, central ventilation. So these central systems come in a couple different forms. You might have exhaust-only systems where you see on the left. So there are exhaust fans that are mounted on the roof. There's a vertical shaft that goes down through the building, and then there are lateral ducts that go off to each one of those units in that particular line that either pull air out of a kitchen or pull air out of a bathroom. There are other approaches where we have more of a balanced approach on the right. So where we still have those vertical shafts that are pulling air out of kitchens and bathrooms, but now we're supplying fresh air into the corridors, so into the hallways, the common areas. And that air may be conditioned, it may not be conditioned, depending on how the building was designed. But the idea here is now we're providing a balanced approach. And typically by design, as we start to introduce air into those corridors, the corridors get slightly pressurized. Air can then make it into the units under the door, and make it towards that negative pressure that is being established by the exhaust fans in the kitchens and bathrooms. So this is an attempt to kind of provide continuous balanced ventilation. Next slide. So some of the issues we find with these systems, the most common one we find is balancing. There was no balancing hardware installed. The quality of the installation was very, very poor, such that it led to a huge discrepancies between the top floor and the bottom floor in terms of airflow rates. Were we meeting the required rates? Are we exceeding the required rates? Are we have no flow, or do we have positive flow? So there's a lot of issues with balance with these larger systems. And some of the effects that Jonathan spoke about, stack, wind, mechanical effect, they impact the ventilation system. So we find that we're competing with those effects when we're trying to ventilate the building, and we start to have a whole host of issues. So as Jonathan mentioned, one of the biggest things that we do with these types of systems, and when you get into larger buildings where stack effect is magnified, building air sealing becomes paramount. We need to be able to control the flows in these buildings in order to improve the ventilation system. I can't be competing with negative air at the bottom of the building coming in and positive air at the top of the building leaving, because it's going to now impact my flow rates, right? The top of the building, if I have a lot of positive pressure because of stack effect, I'm going to be forcing air into the ventilation system. At the bottom of the building, if I have a lot of negative pressure, I'm going to be competing with the negative pressure in the ventilation shaft, and I might even cause air from that ventilation shaft to come out and go into the apartments, and that causes a whole host of issues. So the biggest thing we do with these types of systems to address them from the get-go is going to be to air seal these buildings. Focus on the top, focus on the bottom, control those stack effect driven airflows, and then go ahead and we'll talk about the solutions for the central systems. But typically what we find with central is that the top floor apartments, the top third of the building, is typically way over ventilated. And the bottom third to the bottom 2/3 are very, very, very underventilated. So we have a big, sort of range of ventilation rates. And we have indoor air quality issues because of that. Next slide. So what are the solutions, right? How do we fix this? How do we improve these systems? Next slide. So let's start with natural ventilation. Sorry, one more slide. So while we have to try to provide mechanical ventilation in these buildings, right? They weren't designed with ducts. They weren't designed with easy access to electrical infrastructure. So now we have to get creative and try to find ways that we can get ventilation systems installed in these buildings. So this is an example in a bathroom where we are trying to, we are installing a continuous operating, or not continuous, this is intermittent bathroom exhaust fan. Right. So what do we have to do here? I mean, luckily in this case, we ran into a situation where the ceiling joists are perpendicular to the outside wall. So we had a chase that we could run the duct. So you can see that we cut a hole in the ceiling to fit the fan. But before we put the fan in, we ran duct work across the ceiling there above the plaster ceiling across to the end of that ceiling joist bay, cut down, and then exited the piping out to the outdoors. And we also looked out here. We have a light that is in close proximity, so we were able to pull power from that light. So as soon as the switch is hit to turn the light on, the fan kicks on. So now we kind of control for occupant behavior here. So there's not a separate switch for the fan. So as you turn the lights on, the fan's going to kick on, and then that's going to provide the required airflow when folks are utilizing the bathroom. So again, you have to get creative. And then again, we have to have a variety of trades. We have to interface with the electricians to make sure that we can wire this in. We have to interface with folks that are going to mount the ductwork and install the fans. And then we also need to interface with carpenters that are going to build a soffit in this case to, hide some of these components as they exit the building. So there's a lot of trade and intervention that we have to kind of, control for and have good construction management. And, you might not run into a situation where the ceiling joists are running, perpendicular. They may run parallel. So maybe we have to drop the duct down now, and we have to now build another soffit that goes, across the length. So there's, there's a degree of creativity that needs to happen when you have these types of buildings that are naturally ventilated, where we have to bring mechanical ventilation into the building. Next slide. And then we started to play around with prototypes. We wanted to look at, what are the natural openings in these buildings, and can we incorporate ventilation into those openings? So what you see here is a prototype that we developed with a window manufacturer about 7 years ago. And the idea was, can we incorporate an insulated panel into a window design And can we mount a exhaust fan in that insulated panel so that we can provide continuous ventilation? Because one of the issues that we run into in New York City in particular is that we have a lot of requirements when, if we are going to, let's say, core drill through a building to run a duct, we have to get an architect involved. We have to get permits, and we'll have to install scaffolding and sidewalk sheds and all of these things. So that adds to a lot of the cost. So we were trying to say, okay, can we incorporate this into measures that might be taking place if windows are going to be replaced? Can we incorporate ventilation into those windows so that we can ensure that we're getting proper ventilation and not just relying on that operable window? So this is kind of the early prototype. Next slide. And you can see what it looks like from the outside when it's installed. So there's an operable window on the bottom, and then you have the insulated panel on the top with the fan mounted into that panel. So it's sort of recessed into the outdoors. And then it's a left side discharge to the outside. So we're discharging the exhaust gases to the outside there. And those are running continuously. The newest iteration is the one you see here. This is a prototype we have in our office right now. So here we worked with another window manufacturer to incorporate the ventilation device into the glazing. So now it's, we're not using an insulated panel, we're putting it into the glazing. So it's inside of that, we're installing a casement window. One of the things that we've been doing recently in the weatherization program is looking at ways to incorporate high performance windows in buildings. One for indoor air quality, as well as sound attenuation. We have, a lot of, proximity to major expressways. So we're trying to prevent sound attenuation. We're trying to then improve indoor air quality because windows are one of the leakiest components we find in buildings. So we're trying to, utilize a casement window in this case that can be a lot tighter to prevent a lot of the outdoor pollutants from coming in. And then we couple that with this exhaust fan inside of here, and then that will provide exhaust to the outdoors. Next. Central systems. Next. So central systems, it could be as simple as cleaning, right? So that may be one of the biggest issues that we have, is just to clean the ducts so that we can get flow to come out. So you can see a lot of times dirt does get built up inside of these registers, and we have to clean them out. Next. And then we're looking for areas where they leak, right? We talked about it before. Leakage is one of the biggest issues that we find. So we're looking at all these areas, whether it's at the curb, between the ducts, on the laterals, at the transitions between the laterals and the sheetrock layer. We know that there's areas that we can address the leakage. Next slide. So here's up at the curb, you can see this duct is not even connected to the roof curb, and there's going to be leakage here when that fan is installed. It's going to be pulling air from under the roof deck, not from the vertical shaft. So we want to try to address that and seal that up. Next. Here we drop the camera down and we can see where the duct go, right? We had a vertical shaft that was running down that is the ventilation shaft. And all of a sudden we got to a section where now we have a 5-foot gap between the two sections of duct. So, we have to go in there, open up the walls and figure out, how to fix that. Next. Here is down at the lateral. So this is where the vertical shaft meets the lateral duct that goes off to the unit. Again, there's a hole cut in the ventilation shaft, and then the duct is just kind of just placed in there. So there's a huge gaps around that, that lateral duct that is, allowing air to not come out of the duct, more so behind the wall cavity. Next. And then we have at the sheetrock layer. So when the lateral duct actually comes to the sheetrock layer, a lot of times they fall short, and there's, we're pulling air from behind the wall, not from the kitchen or bathroom. Next. So once we fix those issues and seal all those up, then we want to seal the smaller holes. So we utilize either top left, there's a rotary mastic applicator that spins around and provides mastic spray to seal the inside of the ducts. Or we utilize, or sometimes in conjunction with the mastic, we'll utilize an aerosolized sealant. You can see on the bottom right where we now pressurize the ducts, introduce this aerosolized sealant, and that clogs up all the holes and makes the ductwork much tighter. Next. And then we have the balance, right? So that's just to improve airflow. That's going to improve airflow across the entire, vertical section of the building, but it's not going to distribute airflow evenly. So we utilize then balancing devices like this constant airflow regulation damper to then provide balanced flow. So we're typically trying to push more air or allow more air to be pulled or drawn from the bottom of the building and kind of cut off the upper part of the building. Next. Another option is the fixed orifice. We can use these as well. These are not as dynamic as the car dampers, but these can be used to kind of also dial in the flow rates at those locations where we have overventilation. And the last thing is going to be replacing the fans, right? So when we're done, we want to replace the fans because a lot of times they're old, they're belt driven, like you can see here on the right. Next. And what we want to utilize is, more of a direct drive, more efficient fan. So this is going to help cut down on the electrical cost to run these ventilation systems. We don't want that to be exorbitant. We want to make sure that we have, low cost, ventilation in terms of the operational cost. And then the last thing I wanted to just touch on really quickly was heat recovery. So next slide real quick. So here, what we find in a lot of these buildings is, that, ventilation systems, when they're operating, they also do impact the operational costs from a heating and cooling perspective, because we're taking conditioned air and we're exhausting it to the outside and we're drawing in unconditioned air. Now, wouldn't it be nice to be able to incorporate a device that can exchange the heat energy between those two air streams and cut down on the heating and cooling costs that we have in our buildings? So these heat recovery ventilators do just that. The warm air from the inside on the top right goes through a heat exchanger, and the air coming from the outside that's cold comes in the top left. That goes through the heat exchanger, and then those two air streams, they don't communicate in terms of like pollutant transfer, but they go through this thin membrane where now heat energy transfers between the two, and now the warm air that becomes cold and the cold air from the outside gets warm, and we cut down on the heating or cooling load because they're going to work all the time. So next slide. So we see these, in the units, and this is an example of a unitized system that, we're pulling air out of kitchens, bathrooms, then bringing fresh air into living rooms and bedrooms. Next slide. This is what it looks like in real life in person. These ducts are 3 inches in diameter, so they can be snaked through interior walls, and we can, set them up strategically. Next slide. And then we also have larger systems. So these systems can now incorporate into those larger central systems. We can duct them like this, where we pull air, from the kitchens, and then we exhaust it back into certain areas. So we can use ductwork to be able to facilitate that, the connection between the exhaust and the supplies. And next slide. Or we can utilize a rooftop, a mounted unit here where it'll sit on a curb. This is one that's in our lab that's designed to replace sort of an RTU and sit down right on that curb and connect to the existing ductwork underneath. So there's definitely options to incorporate heat recovery as well to kind of cut down on those operating costs. And then last thing is, this is just my contact information. So if there's any information that we don't cover in the Q&A, you can always, call me, reach out to me via email if you have any additional questions.
Thank you so much, Adam. That was great. That was a really great overview, and I think it gives us a lot of ideas for our own buildings in DC. It certainly did for me. So we are going to turn to your questions. If you haven't already, please go ahead and drop some of those into the chat, and we will get to them. The first question here is, or it's a comment and a question. DC has been working on new window codes for buildings in DC that address birds flying into them and dying. And we're not sure what other jurisdictions that are also dealing with that issue. In your research to address heat loss around windows, are you also taking into account new code requirements such as window designs for various reasons like the birds?
We haven't, but it is a good idea to do that. We haven't had as many issues, but I can talk to some of the window manufacturers and see if that can be incorporated in, but it's not something that we've actively, thought about incorporating. We were just really trying to reduce heat loss and infiltration, near those high pollutant sources.
Got it, thanks. Then I have a question for Jonathan. And you may have touched on this, but in your study, why didn't nitrogen dioxide decrease significantly in the study's ventilated units?
Yeah, that's a challenging question. And so I don't really have a precise answer. I think we would have said if we knew. We did see that there were, definitely higher pollutant levels in these two communities. So it could be outdoor air that, and nitrogen dioxide is a reactive gas. And so we know that actually if you have ozone in the air. It can actually react and create nitrogen dioxide as well. So there are a lot of different factors, when we think about air quality, that it's not just the indoor sources that are creating the indoor air quality problems. It could be that we're bringing in outdoor air. And, I was thinking about that when Adam was presenting his heat recovery ventilator. We read a study, or I read a study in Chicago where they failed to put in filtration on their supply side. And they actually found that they created more problems in the property with the small particulates coming in. So it's critical that when we think about ventilation, we also have to think about filtration as well. I think Leslie, in your opening remarks, you mentioned that. That's critical.
Yeah, that makes sense. Thank you. We had a couple of questions for Adam around that automatic bathroom exhaust fan. One question was, and I think this question related to that automatic system you were talking about, how much, like on average, how much might that cost? Sort of ballpark figure. I don't know if you can quote this off the top of your head for a typical unit to install an automated system like that.
Yeah, so I mean, the largest cost is going to be bringing an electrician in. It's trying to find a source of power. So we lucked out here where it was very close proximity to the lighting fixture, so we can pull power from that fixture. But sometimes we have to bring power to the fan, to the device. Let's say in kitchens, so we might be able to look for a receptacle nearby where we can pull power from that. So those costs, I mean, it depends. Like, this is New York City pricing, so maybe $800 to $1,000 to bring an electrician in to spend a few hours running wire and fishing it through. The fans are not that expensive. They're maybe $150. They're not super expensive. The ductwork is fairly inexpensive, and then there's a little bit of carpentry work. So where we luck out on our side for the implementation end of it is that we have in-house crews, and a lot of this work is done through the Weatherization Assistance Program. So those crews are providing that labor. So the only thing that we really have to outsource or pay for is the material and the electrician's cost to wire the unit up.
Got it. Thank you. And then I have another question about those automated systems. What's the life expectancy of the inside continuous exhaust fans? What maintenance is needed to maintain them?
So the life expectancy is pretty long. I mean, right now the fan technology has come, so far. I mean, right now we have a lot of electronically commutated motors. I mean, for instance, I have a continuous operating fan in my house, and it's been running for 10 years and hasn't failed. But the issue with continuous ventilation is that you are going to be drawing a lot of air into that fan, and any dust, debris, particulates that are in the air are going to stick to that fan grill. So periodically you have to maintain those and clean them off because they will plug up fairly quickly. And you can see even on the central system that I showcased that those grills were covered in dirt and debris, especially in kitchens. When you're cooking and you maybe frying something, you get a lot of grease into the air, and that sticks, and then any dust or debris gets stuck to it. So cleaning is a big thing to try to make sure these systems stay functional.
How often do you recommend that cycle of cleaning?
So it depends on usage. Like kitchens, I would say every 6 months, because it's generated more. Bathrooms could get by maybe every year, but I would say, at least every 6 months to assess them to see how dirty they are and see if they need to be cleaned. Because what you don't want to do, especially with the localized fans, you don't want to have that dirt and debris get on the fan itself, because then it'll start to overheat the fan, and that can lead to premature failure.
Another question, there's a wide range of ASHRAE 62.2 ventilation levels, depending on the year of ASHRAE 62.2 you utilize. Are you aware of any studies comparing contaminant levels based on different ASHRAE ventilation levels?
Right. I mean, the standard that we're following is the 2016 version of the standard, and that's what Weatherization has adopted. And right, if you go to look at the 89 standard, or if you look at the new standard now, it is a continuous maintenance standard. So they revise the flow rates based on industry feedback, which is great. But I haven't looked at any. I don't know of any studies that might have looked at the different rates. I know that they've been getting more precise over time. based on feedback, based on the maintenance committee, which I've interfaced with. So I would imagine the newer standards are, are really the most up to date and in terms of flows and most impactful.
Yeah, we were involved with a study with the University of Illinois that was looking at the ASHRAE 1980, 19, yeah, was it? Sorry, Adam, which level were you're saying?
89 was one of the ones that was also widely used, and then we started to see
89. We compared as our baseline, and then we compared it to a newer standard. So that study is out there, and I know it's available. The I don't know of any others that have looked at more recent, but I think that there's been more tweaks recently than really major changes. So I'm not sure that investing in a study would be that useful, since it's fairly minor changes between the two as far as the ventilation flows go.
Another question in the chat. With the integrated window fan unit prototypes, can the fan units be changed out in case of fan failure? Or would the entire window need to be replaced?
Right. So we thought about that as part of our design. So in both of those prototypes, the earlier one and the new one, the fans can be replaced. Just the fan module itself, because that's what typically would fail. So you can disassemble the housing and then just replace the fan. There's a lot. The newer one has just a Molex plug. You just unplug it, plug it in, put the new fan in, and you're good to go. So it's but they're designed to be very long-lasting fans. That was the idea was part of the prototype, is that we don't want them to have a lot of maintenance, as maintenance free as we can make them is was the idea. But we wouldn't have to replace the window or the unit itself, just the component that failed.
Another question here. We see a lot of exchange air grills installed between rooms in a new multifamily building. Would this be helpful in older construction to obtain a continuity of airflow throughout units, despite the sound concerns between the rooms?
Yeah, so we look at that as well. So one of the components of the 2016 ASHRAE standard is to make sure that we do have good airflow between adjoining rooms. So if we are installing a exhaust fan that is going to be centralized, we need to make sure that it's properly ventilating or drawing from all of those locations. So what we'll do is we'll close the door between, let's say, a bathroom and the living space, or between a bedroom and the living space, and then we'll measure the pressure difference between the two. And if it is great, greater than a certain range, then we have to make, modifications to allow airflow through there, which might be a transfer grill or something like that, to your point.
We have a question for Jonathan about the study. Was it ASHRAE level 2 or 3 audits that were performed?
Yeah, unfortunately, I don't know that. We went in to do the testing after the work had been done. So they had the green rehabs done sometimes as far away as 8 years before we were in there. So the actual process of doing that was not part of our study. What we did do is we used a ventilation consultant who came in, looked at the flows, and said, yes, this is higher or lower. So we were not going into the buildings and doing the work ourselves. We were taking existing paperwork and making a judgment based on that.
And I just had a question. I'm guessing that the buildings, Adam, that you addressed that were natural ventilation buildings, are these typically, like in DC, these are the low-rise buildings up to 3 stories kind of thing?
Yeah, I mean the predominant housing typology in New York that is naturally ventilated is our 6-story kind of walk-ups. So they're kind of like a lowish rise building. So they're the ones that are the ones that were built pre World War II, and those are the ones that we typically find that are naturally ventilated.
Yeah, in DC we have a lot of these brick,
Right.
new buildings, 3 stories. They usually have bathroom and kitchen, exhaust, but no central.
Right. And that's very similar. Like they're masonry constructed, it's
Yeah. I think Jonathan's just dropped an ASHRAE study into the chat. I think some people were asking about that earlier. So that's helpful. Thank you. So with that, I think I will turn this back over to Susan to wrap us up.
Thank you, Leslie, and thank you, Jonathan and Adam. Just want to give oh, you can't see me. Just a quick reminder that we do have part 3 on pest, mold, and muck coming up next Wednesday. Same time, but different day of the week from 11 to 12:30. We'll have 3 additional great speakers for you guys for part 3. Before you log off today, if you can just give us some quick feedback on today's session. We got a lot of great questions and feedback on session 1 that we were able to build on today. So we're hoping to do the same for part 3. Today's session was recorded, and we will provide the slides. Once you fill out the survey, you'll get a link to the slides and the recording later today. So please, please, please fill out the survey and give us your feedback as we do take it into account as we're planning additional sessions. So with that, I just want to thank NHT again for all of their hard work on putting this session together. Thank you, Leslie. And thank you again, Adam and Jonathan, for taking the time out of your day to share with us. Like I said, you'll get the slides, so their contact information is in there if you have any additional questions for them. But with that, I want to wish everybody a great rest of your Thursday. Happy Halloween, stay safe. And again, if HAND can be a resource to you in any way, don't hesitate to reach out. Thanks, everybody.
Thank you. Bye-bye.
Bye.